Alright, silly people, here's the situation. We have a potential that's like half of a finite square well. It has a width of A, and it's got the potential minus V naught, um, where V naught, I wrote it minus V naught here, but it's actually just minus this constant here. And we need to find how many bound state solutions there are, and as well talk about how likely it is to find the thing outside of the well, right? So the thing about this is that it's finite square well. So before you even think about the fact that the other side is infinity, you can be like, oh, there's the even solution and the odd solutions. But you only admit the odd solutions because if this is the potential, you have to have that the wave function is 0 at x less than 0, because it's in an infinite potential. So that means you can only admit the odd solutions because the odd solutions are the ones that cross 0 as x equals 0, right? So those odd solutions were in a couple different regions: f e to the minus kappa x for x greater than a, and then d sine lx 0 less than x less than a. And then um, this is a familiar problem to us because we did like a bunch of stuff with the odd parity solutions for the bound states in question 29. So we're very well prepared for this. And if you haven't watched it already, I recommend going and watching that because you're going to be using a lot of results from that, and I'll mention them as they come up. Um, so to be a solution in this potential, well, first you have to be the solution of a bound state. So E definitely has to be less than 0. Um, but also E always has to be greater than V. So E has to be somewhere up here, which means E has to be E has to be greater than minus V naught, which means E has to be less than V naught, right? So um, we found out from 229 an expression for E plus V naught, not just E. So I'm going to write it like this: E plus V naught is less than 2 V naught. And then this is something that we got from problem 29, was that E sub n plus V naught was approximately just n pi h bar over 2a all squared divided by 2m, for n being any even number, right? So on the left-hand side of this inequality, we can write this thing. So we'll do n pi h bar over 2a all squared times 1 over 2m is less than 2 times this value, so 64 h bar squared over ma squared. All the constants get canceled out, and we just have n squared pi squared over 8 is less than 64, and then we can do the little solve here. So n is going to be less than the square root of 64 times 8 over pi squared. And I found that that was about 7.202 on my calculator, so has to be less than 7 pretty much, which means we got 2, 4, and 6 are all less than 7, so we have 3 bound states corresponding to n equals 2, n equals 4, and n equals 6. Um, Now I have to do the probability thing. So first of all, we need to normalize it. We didn't do that in problem 229. So we'll have 1 on the left-hand side, and on the right-hand side, we have the mod squared of the wave function, which, since we have two regions, we have to write the integral in a couple different regions. And this is plus, and that's dx, plus mod f squared integral a to infinity e to the minus 2 kappa x dx. Yeah, that's fine. So this is pretty standard stuff here, I think. We'll use this relationship between sine squared and cosine. Sine squared theta equals 1 minus cosine 2 theta over 2. Pretty good identity there to do the integral. So we have that it's mod d squared over 2. And then in here we have the integral of just dx, and then minus the integral cosine 2lx dx from 0 to a, and then the exponential integral is pretty easy because it's just e to the minus 2kx over 2k. It's over minus 2k actually. Yeah. I'm going to say k and kappa interchangeably in this video. Just fair warning. I mean kappa. So let's do these integrals. D squared over 2, 1 minus 1 over 2l sine 2lx from 0 to a. This turns into just f squared over 2 kappa e to the minus 2 kappa a. Plug these in over here. We have 1 minus 1 over 2l, just sine 2la. And it's not 1, is it? Because this is x. So this is a. Yeah. But that looks good now. So a thing from 229 which we haven't used yet was the result of the boundary condition that the wave function is continuous at x equals a. And that turned out to be, I'm going to write it in blue, that turned out to be f equals d e to the kappa a sine la. So we're going to use that. So rewriting the normalization integral, 1 over 2l sine 2la plus, and let's even try and reduce that sine 2la because we also have the trig identity of sine 2 theta equals sine theta cosine theta, or 2 times that anyway. So we can write this as 2 sine la cosine la plus mod d squared over 2 kappa. And it'll be e to the 2 kappa a sine squared la e to the minus 2 kappa a. And so the exponents will actually cancel out, and that's nice. We can group it all together. So we'll get stuff which depends on mod d squared over kappa a, and then in the brackets, or not over kappa a, over 2 kappa. That's what we're going to do. So we'll have kappa a minus k over l sine la cosine la plus sine squared la. I'm going to introduce a new definition, also from 229, but also like in the chapter, that z equals LA. And another boundary condition result, we found that minus k over L was equal to cotangent of LA. So, or cotangent of z by that definition. So we've got mod d squared over 2 kappa, kappa A plus cosine z over sine z, sine z cosine z plus sine squared z. And then bada bing, bada boom, those signs cancel out. And then we get in here, it's kappa A times, or kappa A plus cosine squared plus sine squared. That's equal to 1. So we can write it as kappa A plus 1. Nice. So at that point, I think it's good to go ahead and solve for d squared. I'll leave it as mod d squared, and then it's going to be just 2 kappa over kappa A plus 1. Awesome. Now that it's normalized, we can go back to the probability, which is going to be the integral of the mod squared of psi from a to infinity. So again, that's just mod squared a to infinity e to the minus 2 kappa x dx. We already know the result of that integral. So let's expand the definition of f again as d squared e to the 2 kappa a sine squared z e to the minus 2 kappa a. Yep. And it's all over 2k. 2 kappa even. According to what we just found from the normalization, we can rewrite this as sine squared z over kappa a plus 1. There's a fancy way that we can rewrite the sine function, since it is just sine squared theta over 1, which means it's sine squared theta over sine squared theta plus cosine squared theta, which means if we divide both the top and bottom by sine squared, you get 1 plus cotangent squared theta. And we happen to have a nice form for cotangent squared theta, that is, cotangent theta was just minus k over L. And then there was a fancier way to write this, again going back into Griffiths a little bit, but you can define another variable, z naught, which was just a over h bar square root 2m v naught. And again, z was just LA, so this turns into, down here, minus the square root of z naught over z squared minus 1. So putting that all back into the probability, we still have the 1 over kappa A thing. That's not going to go away immediately. But then we have 1 over 1 plus cotangent squared z. And this is actually z here. So we'll rewrite it like this, kappa A plus 1 over 1 plus z naught over z all squared minus 1. but then those 1's cancel out, and we just end up with the z squared on top, and also z naught squared multiplying the bottom. So sort of like that. Also, interesting way to rearrange the definitions of z and z naught that Griffiths did was that kappa A was equal to the square root of z naught squared minus z squared. So let's do the same thing. So finally we have z squared over z naught squared times the square root z naught squared minus z squared plus 1. But what are actually z and z naught? Well, going back to how z naught was even defined, this guy over here, both of the times that z naught is mentioned, it's actually squared. So let's do the square of this. Z naught squared equals a squared over h bar squared times 2m v naught. And from the problem statement, we know that v naught is 32h bar squared over ma squared. So we have a squared over h bar squared times 64m, and it's h bar squared over ma squared, so it's just 64. All those constants cancel out. That's fun. And then z is the solution that you have to find by doing a transcendental equation. The equation in mind was that cotangent of z equals the minus the square root of z naught squared over z squared minus 1. Remember, that's the boundary condition. So if you go to Desmos and then you rearrange this so that it's like cotangent x plus square root z naught squared over x squared minus 1 equals y, and then like plot it and find the points where it crosses the x-axis. And it is actually going to cross at 3 points because it is like a crazy trig function. There's going to be here, and then here, and then here. These correspond to the n equals 2, n equals 4, and n equals 6 states. And you want the highest energy thing according to the problem statement, so you use the n equals 6 solution, which I found was about 7.9573. So if you square that number, that's going to give you z squared to plug into here. And once you do that, you have that the probability is equal to 7.9573 all squared over 64 square root of 64 minus 7.9573 all squared plus 1. And I plugged this into my TI-89, and I got something like 0.542, like Griffiths got. So I think we're pretty good there. A lot of mental gymnastics, this problem, but I think it's a good one.